In this session, we will build a neural network using PyTorch. First, let's understand what a neural network is. An animal brain contains neurons, the cells responsible for processing sensory input from the external world. Neurons are interconnected so that they can relay signals to each other. As such, neurons form a network of neurons, which we call a neural network. Inspired by biological neural networks, an artificial neural network is a collection of connected nodes, which we call artificial neurons or simply neurons. Neurons are typically organized in layers. The input layer receives input data, intermediate layers or hidden layers process data through connected neurons, and the output layer holds the final values. Neural networks can represent many functions. For example, a simple linear regression is a neural network without a hidden layer. We have input X, weight W, and bias B. The output layer with one node calculates the y-hat. This is another example of a neural network. It represents a logistic regression with two input values, x1 and x2. There is a weight for each input value and a bias for the node in the output layer. It also applies a sigmoid function, which we call an activation function or simply activation. The final output is an estimated probability. A neural network can represent more complex functions using hidden layers. The rule is simple. Hidden layers and the output layer accept inputs from the previous layer. A layer uses a weight for each input, a bias for each node, and an activation function for the layer to calculate an output for the next layer. I'm using superscripts to indicate which layer the weights and biases belong to. This subscript indicates the weight is for the first node and the first input value x1. This subscript indicates the weight is for the first node and the second input value x2. This subscript indicates the weight is for the second node and the first input value x1. This subscript indicates the weight is for the second node and the second input value x2. In other words, weights and biases are organized into a matrix and a vector per layer. The first row of the layer 1 weight matrix contains the weights for the first node. The second row of the layer 1 weight matrix contains the weights for the second node. The biases are for the first and second nodes, respectively. The hidden layer uses the weight matrix and bias vector to perform the linear operation and then applies the activation function to produce the outputs, which then become inputs to the output layer. The output layer contains one node with two weights and a bias. An activation function is optional for the output layer. It uses the weight matrix and bias to perform the linear operation. If there is an activation function, it applies the activation function to produce the final output. Activation functions are nonlinear, and any hidden layer should have an activation function to introduce nonlinearity in the network. But why do we need nonlinearity? An analogy might help. Suppose we have 2D data points where a model needs to classify them into two classes. A linear function can draw a decision boundary like this. We can use a logistic regression model for such a binary classification problem. How about this? We have 2D data points with nonlinear boundaries. A linear function cannot draw a suitable decision boundary for this. We would need something like this to draw a boundary. No matter how we try, a linear function cannot do this. But you may still ask, why do we need an activation function in each hidden layer? Can we only have one activation function in the output layer and be done with it? Let's remove the activation function from the hidden layer and see what happens, shall we? The hidden layer performs the linear operation without an activation function to produce an output, which becomes an input to the output layer. We can rewrite the equation using the hidden layer weights and biases. Then, we rearrange the terms for input x and the rest. Multiplying two weight matrices produces another matrix. Let's call it W dash. The remaining term becomes a new bias term. Let's call it B dash. Therefore, the hidden layer weights and biases are combined with the output layer's weights and a bias. So, we ended up with a linear operation as if we don't have a hidden layer in the first place. This is why we should have a nonlinear activation function in the hidden layer to increase the complexity of the neural network. PyTorch has many activation functions. They introduce nonlinearity into a neural network. ReLU is most commonly used in hidden layers. It returns x when it is positive. Otherwise, it returns 0. Historically, the sigmoid function was used as an activation function for hidden layers. However, the sigmoid function has diminishing slopes towards both ends. As such, the sigmoid function suffers from the vanishing gradient problem, where the partial derivatives become too tiny, and the network learns too slowly. On the contrary, ReLU's slope is always 1 when the input is positive, where the gradient is less likely to suffer the vanishing gradient problem. ReLU allows the network to exploit the positive value range. We can make a deeper neural network by adding more hidden layers. If a neural network has 2 or more hidden layers, we call it a deep neural network. That's it for this video. I hope you enjoy learning how a neural network works. Bye for now.